As David mentioned, I'm with the NASA Solar System Ambassador Program. We are an outreach part of NASA to bring information about NASA to everyone. And we are volunteers, but we are still a NASA program and subject to all the NASA rules and budgets and all that sort of stuff. So grab the swag while you can. Webb was launched Christmas Day, 2021. And they called it a Christmas gift for astronomers. I think it's really a Christmas gift, not only for them, but for all of humanity, because we're going to be able to see, going way back in the formation of the universe, what things were like and where we came from. A telescope such as the Webb and such as our beloved Hubble is really a time machine, because you're looking back at time. When you look up at a star, for example, if that star is 2,000 light years away, you're not looking at that star as it appears today. You're seeing that star as it appears 2,000 years ago, the time that it took the light to reach us. And with Webb, we're going back billions of years. So that's going to tell us a great deal about how the galaxies formed, how the stars formed, and where even our little corner of the universe came into being. For example, this little rock right here is, hold it. This is a rock that was flying around in our neighborhood prior to the formation of the solar system. So the solar system is about 4.5 billion years old. So this was part of a large asteroid that is over 4.5 billion years. It fell to Earth about 4,000 to 5,000 years ago in Northwest Argentina. And the natives in that area were using it to make tools, because that's iron. So they were using it to make tools. The Spanish explorers came by, and the natives said, "Hey, let me show you something cool." And they showed them this big rock. It was actually the asteroid that this came from, and it's called Campo del Cielo. Don't ask me what it means in Spanish. I know it has something to do with field. And prior to the 1960s, or actually in the 1960s, the only way we could find things out was to send robotic missions and people, Apollo, to various places, such as the moon. These two are actually Apollo core drills that were on the moon that took samples and that were brought back here to Earth for us to figure out what they're made of and was there any similarity with Earth. And what we discovered when these two plus all their little brothers and sisters came back is that we have a lot in common with the moon, meaning that the moon was once part of the Earth. And the way it was formed is by a mass collision. There was a Mars-sized planet that careened into the Earth, spread out debris from the Earth and from what is known as Theia, that Mars-sized planet, and it formed a ring around the Earth, similar to Saturn. That all coalesced into what we know as the moon. The moon was much closer to the Earth, and so the Earth day, I think, was about 8 hours long to start off with. So if you think 24 hours is enough time in the day, picture 8 hours. So let's get into Webb, because that's what you're really here for. I'll explain all of these during the presentation, but this is just a sample of what it's found in less than a year. I have to give this usual spiel. I'm with the Solar System Ambassador Program. Any opinions that I give are my own. Don't blame NASA for it. So moving right along, Webb is going to see farther than any other telescope that we have, including the Hubble. And Hubble saw pretty far back. Webb is a project that many countries took part in. So as an example, we have the United Kingdom, Ireland, Netherlands, Belgium, France, Spain, of course, the United States, Sweden, and you can see them all here. So this wasn't just one country doing this. This was a collaboration of many countries to bring this about. So really, it's humanity doing this. And this is a video about putting it together. No, it's not. Let's try it this way. Yep. Okay, we tried this before. Okay. Oh, there we go.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown, a 5-layer, tennis court-sized sun shield that blocks heat from the sun, Earth, and Moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
A couple of things about that previous video. Webb was launched on an Ariane rocket, which is a French rocket, and it was launched from French Guiana. The reason why it was launched from French Guiana is because it's near the equator, and the Earth spins faster at the equator. And it was also launched towards the east. And what that means is you could use the rotation of the Earth to give you a boost, almost like if you're pushing a kid on a swing. It's similar to what this is about. And that's why when you see any launches from Kennedy Space Center, they're going east to get that boost from the rotation of the planet. This is just a graphic about the beginning of the universe. We have inflation. That's the other thing I wanted to mention. That person mentioned Big Bang. Now I'm going to blow your minds a little bit. There was no Big Bang. There was the big inflation. Nothing banged, because if it banged, stuff would have gone everywhere and we wouldn't be here. So it really inflated like a balloon. And it started 13.8 billion years ago and moved into the first light, which was about 375,000 years. The dark ages, before that, we couldn't see anything. Then galaxies, planets started developing. And now the universe is still expanding. And it's expanding because of a mysterious force called dark energy. And that dark energy, we don't exactly know everything about it, but it is making the universe itself expand. So the universe is expanding faster than the speed of light. So to give you an example, okay, let's say this is the universe, the fabric of the universe, and it is a fabric of time and space. It's actually moving out like this, and it's taking the galaxies with it. The galaxies themselves are not moving, but the space-time fabric is the thing that's moving, and therefore the galaxies go with it. So in a couple of trillion years, we are going to have a dark universe if this continues. This is called the cosmic microwave background radiation. This is a universe's baby picture. This is the equivalent of us at 7 seconds old. And it has blue and red spots. The blue spots are the cool spots in the universe. The red spots are the hot spots where everything comes together. This was discovered by 2 scientists with Bell Labs in Homedale, New Jersey. And it's an interesting story. They were trying to figure out how to bring signals, radio signals and television signals to rural areas. And they kept getting this hum out of this big horn that they were using. And they couldn't figure out what the hum was. So they called the local air base, and they were told, no, it's not us. The local army base, who said the same thing. And the myth is that they were at a conference and talking about this. And somebody raises their hand. Oh, wait, before they were at the conference, they thought, okay, pigeons were nesting in the horn. So it was pigeon poop that was causing it. So in an unpleasant task, they cleaned it out of all the pigeon poop, these 2 scientists. And so then they went to the conference, and somebody raised their hand and said, well, it's one of 2 things. One is you found the effects of pigeon poop. The other is that you found the signature of the Big Bang. Now, why do we call it a Big Bang if wasn't a Big Bang? It was more of a big inflation. Well, back in the 1920s, there was a father, George Lemaitre, who first proposed the inflation. Then along comes Edwin Hubble, who verified it, that galaxies were moving apart, but it was because of space expanding. And another scientist by the name of Hoyle in the 1940s didn't believe it. So insultingly, he said, yeah, sure, there was a Big Bang. And we've known it by that name ever since. So when we talk about the Big Bang, we don't really mean a Big Bang. We mean a big inflation. And this is the launch of the Webb.
Standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Trajectoire est nominale.
Vehicle performance is nominal.
Nominal meaning there's no problems.
The Ariane
Things are
5
going as
rocket
expected.
continues to fly uphill in nominal fashion.
And here's another video. This is how the Webb was deployed. They were talking about in the previous video, in a couple of previous videos, a couple of slides before, that it was folded up like origami. This is the unfolding. This is a very delicate operation that took a long time to get correct. This is the sun shield that's unfolding. When it was unfolding in space, they had a hitch. All of a sudden it stopped. And they thought, uh-oh. So they tried various things to get it to go, but they had to be very careful, because if they ripped the sun shield, that was the end of the telescope. But they were able to get it. It was a stuck hinge. So where is it? In space, there are points. There are 5 what we call Lagrange points. And that's where the gravity of 2 bodies equal out, so that whatever you place in that point will stay stable. You don't have to worry about fuel or it straying off course. And this is what we're at the number 2 Lagrange point, and this is what it looks like in relation to the Earth. So you can see Webb in that L2 designation moving along with the Earth. And that is about 1 million miles away. There are 2 sides of the telescope, the hot side and the cold side. The hot side, of course, faces the sun, and it's at 185 degrees Fahrenheit. That's where the solar panels are, the communications antenna, computer, steering. the reaction wheels and jets. The cold side, on the other hand, is facing away from the sun, and that's at minus 388 degrees Fahrenheit, and that's where the science instruments are. They have to be very cold in order to operate properly. And then there's detectors and filters, and that's where the mirrors are. So we're going to explore the universe with Webb. Redshift, that's how we can peer into the cosmos. When something is moving away from us, it goes to the red part of the spectrum, which I'll explain in a slide or two. But the further out it goes, the redder it gets. The further in it comes, the bluer it gets. And redshift is a part of the spectrum that allows us to see right through various dust and gases so that we can get clear pictures. And you'll see those clear pictures in just a minute. So in the light spectrum, there's gamma rays, X-rays, like we all get when we go to the dentist or the doctor's office, ultraviolet light, the UV light that gives us a nice sunburn, visible light, which is a very small part of the spectrum, infrared light, microwaves that we use to zap our food, and radio waves. These are all forms of light, and these all make up the electromagnetic spectrum. And there it is, the gamma ray, X-ray, and you can see the small sliver for visible light. But as you move into the infrared, that allows us to see very clearly, what's out there. So spectroscopy is taking the light that's emitted by various objects, could be stars, planets, and matching the light that we see, the color of the light, with the elements. So the periodic table, a listing of elements, we match what the colors that we see with that periodic table, and we could tell what's in the various pictures that we're seeing. Oxygen, nitrogen, methane, things like that. And this will give us an idea as to whether a place could harbor life.
How did we get here? Big questions about who we are and how we got to be that way are at the core of our nature. We've developed technology to see amazingly far across space and also time. Light moves through space, just like we do, only much faster. It takes time to get somewhere. So, viewing the light of distant stars and galaxies is like looking into the past. It took time for the light to reach us. Yet, after all our years of exploring, to better understand ourselves and our origins, there is still so much to know. Our story stretches back more than 13 billion years, not long after the expansion of time and space first began. At some unknown time, the building blocks of life were forged in the heart of the first stars. But much of the early universe remains a mystery. There are theories about how gravity first brought stars, gas, and dark matter together to form galaxies. But that time period has never been observed. Detecting light from the first galaxies to form has been a challenge for even the most powerful telescopes. As the light early galaxies emitted traveled through space, that space itself was expanding, stretching the light to longer infrared wavelengths. Past telescopes have detected infrared light, but the faint light of these very first galaxies has remained out of reach. until now. The James Webb Space Telescope is specially designed to detect the first galaxies. Webb's large mirror and sensitive instruments will enable it to collect more infrared light than we've ever seen, allowing the first galaxies to emerge into view. With Webb, we can begin filling in some of the blank pages at the beginning of the universe's story. When did the first galaxies form? How massive were they? What types of stars and elements did they contain? The universe's story is our story. And with Webb, we can finally explore these questions, as well as uncover new ones we haven't even thought to ask.
A couple of things. One is, are we ever going to be, excuse me, able to see what happened at the Big Bang? And the answer is no, because there was no light. In the Big Bang, or Big Inflation, everything came out of a subatomic point in space. How everything came out of there, we haven't figured out yet, but we can't get back to that moment in time when space started expanding, or when space and time started, because everything was so hot back then that light photons, which emit light, were unable to come together. So without the photons, there was no light, and therefore the furthest we can get back is that cosmic microwave background radiation, 375,000 years after the Big Bang. But with Webb and Hubble and the Spitzer telescope, we've been able to go pretty far back and see how those first galaxies formed. But we will not see how the universe came into being, unfortunately. And then there's a question of what was there before the universe? And that's the hot topic. Yes?
Who was James Webb?
James Webb was an administrator of NASA, which is the head person at NASA. He was the one that was responsible for getting us to the moon. So he was responsible for the Mercury, Gemini, and Apollo programs.
Why was gold used on the Hubble, on the Webb?
Gold is a highly reflective substance. Those things are polished beyond polished, and that's how it collects the light. A telescope, the way it functions is it collects light and focuses it to a point. That's why if you see somebody with a telescope, the light is coming into that telescope being focused to a point. And that's why you can't look directly at the sun with a telescope, because you will be instantly blinded, because it's so powerful. You need a special filter and all that sort of stuff. But that's the way we gather the light. And it looks nice.
What is the surface of the Hubble telescope? If the Webb is gold, what's the surface of?
It's just a mirror, from what I understand. And Hubble had its own problem. Back in 1990, when they launched it, they discovered that one of the mirrors was polished incorrectly. It was off by the width of a human hair. And so the pictures were blurry. And that's why we sent astronauts up there to repair it. Somebody came up with the idea of, well, if it has an astigmatism, why don't we fix it with glasses, just like a human? So they went up and they fixed it. So in this essence, Hubble has glasses. Staring deeper into space. I mentioned that telescopes are time machines. There's another time machine that we all have, our eyes. Because when we look up, we see the stars. And as I mentioned, we see the stars as they were, based on how far they are. In fact, we're just a short distance from each other. We're not seeing each other at exactly the same moment because it takes light time to travel from where I am to where you are, and from where you are to where I am. Okay, so let's see if I can get this one. These are just amazing pictures. All those little points out there are galaxies. So the question becomes, all these are galaxies. What do the statistics say about life elsewhere? In my opinion, there has to be life somewhere in the universe. There's just too many galaxies out there. And every star that you see in the night sky has planets going around it.
Each galaxy would have, let's say, 200 billion stars. Is that a good estimate?
I've seen 100 billion and I've seen 200 billion. I'm going with 200 billion just for the heck of it.
So each one of those bright spots is representing at least 100 to perhaps 200 billion stars.
Right. And the number of galaxies we thought was 100 billion. But with Webb, one of the project people that we just don't know, Webb is showing us so much more that it's probably not 100 billion.
Each star we looked at as planets, whatever.
Yeah, on average, there's at least one planet for every star. We have 8 planets. There are other stars with several planets also. The question is a planet right for life? Does it have water? Because water is the essential ingredient of life. Does it have the correct atmosphere? And that's what Webb is helping us figure out.
Well, if we look at the North Star has planets going around it.
Has at least one planet. Okay, this is the good stuff, the pictures. This next one is Cosmic Cliffs, which is in the Carina Nebula. As I mentioned, a nebula is a star nursery. This is where stars coalesce from dust and gas, dust being small grains of rocky material, or things like that. Gas, hydrogen is the most prevalent element in the universe. So that all comes together and forms a star. And it forms a star because of gravity. So that's what it looks like. And you can see all the blue stars. There's a baby star. There's another one in there. You can see a whole bunch of little baby stars being born. And this is the same nebula, but from Hubble. You can see it's not as distinct as Webb's. That was a creation. Couldn't think of that. That's the one that I'll be showing. Okay, the next one, perfect time of the year for this. Anyone see the movie It's a Wonderful Life? At the beginning, there are galaxies talking to each other. They're supposed to be angels.
Yes.
These are the galaxies. This is what they use. Stephen's quintet. And we're going to take a close-up view. Unfortunately, they're not going to be talking. That's 290 million light years away. Light year is not a measure of time. It's a measure of distance. Light travels 186,000 miles per second, a little bit slower than how fast I go in my car. But so in a year, light travels 6 trillion miles. So Stephen's quintet is 290 million times 6 trillion. The observable universe, from one end to the other, is 92 billion light years. So again, 92 billion times 6 trillion gives you a number with a lot of zeros. And there is something beyond that horizon that we will never see. This is the Southern Ring Planetary Nebula, again, the nursery. The shells of gas and dust ejected from dying stars. So these are stars that have exploded. And just to give you something interesting about exploding stars or nebulas, everything that we have here, the building, the floors, us, came from nebulas, supernebulas, because they eject all the materials that are needed to make up the universe, what we see in the universe. So we are, in effect, stardust. And the stardust in my left hand could have come from one nebula, and the stardust in my right hand could have come from another. And that's how we get the materials to build everything. So another example would be, somebody asks you how old your car is. It's 13.8 billion years ago, because it was born from the universe. And that's the Southern Ring Nebula. And that's how, this is a chart of how we figure out what's out there. So you can see that it has water, and where there's water, there's a possibility of life. There's a whole bunch of other factors, but water is essential for life because it's a solvent. It takes the building blocks of life and mixes it. For example, if I were to make a cake, and I took eggs, flour, sugar, and whatever else you put in the cake, and throw it into the oven without doing anything to it, I would wind up with a glop. I need some kind of medium to bring it all together. And that's what water does for life. And this is Webb's first deep field. And it was captured in 12.5 hours. And I'll compare that in another slide with Hubble to show you the difference between the two. Again, take a look at all the galaxies. And you see this line right up here? That's the galaxy behind that galaxy. When light is emitted, if it runs into something, it's going to take the path of least resistance. So if I had a light, for example, that I was shining here, you'd still be able to see it because the light will go around this rocket. That's what happens out in space. And that's how we can find other galaxies. Hubble, on the other hand, took 10 days to capture this picture, which is the similar space as the one we just saw. When they took this with Hubble, somebody said, there's empty space out there. Let's see what we could find. So they pointed Hubble in that direction for 10 days. And this is what they ended up with. So space is full of galaxies, stars, planets, things like that. But if you take a look in between, you would think that there's empty space. There is no such thing as empty space. And there's no such thing as zero gravity. There's always something there. I had mentioned quantum mechanics before. These subatomic particles, they're out there. These particles can zap into existence, and in a fraction of a second, zap out. And that's, they create gravity. So there's no such thing as zero gravity. It's microgravity. And this is gravitational lensing. That's what I was showing you before, that galaxy behind the galaxy. So you could see that the sun was blocking out a star, and all disappeared. You know, galaxies there. This is what actually proved Einstein's theory of general relativity. He needed this person, Eddington, to go out to Africa and wait for an eclipse. But that's an eclipse, and because of that eclipse, he was able to see the light being bent around the moon. And that proved Einstein's theory of general relativity, which dealt with gravity. And that light will follow the course of least resistance. And then this is just using spectra to identify galaxies when the universe was much younger than it is today. So you can see galaxies 11.3 billion years, which come down to here, and then 12.6 billion, 13, and 13.1. As we get younger, we can see that they're starting to form. And that's what Webb is going to be picking out, how they form. And this galaxy emitted its light 13.1 billion years ago. And that's this one right there. And within that galaxy, there's oxygen, and hydrogen, and neon. And this is the Cartwheel galaxy, formed 440 million years ago because of a high-speed collision. And we're going to zoom into it. Oh, okay. This is the farthest known galaxy so far, 13.5 billion years old.
The James Webb Space Telescope may have discovered a galaxy that existed 13.5 billion years ago. A scientist who examined the data claimed Wednesday, only a week after its initial images were made public. Known as Glass Z13, the galaxy dates back to 300 million years, after the Big Bang, about 100 million years earlier than anything previously identified, since it takes longer for light from distant objects to get to us. Looking back at the distant cosmos is like seeing deep into the past. Even though Glass Z13 was a part of the universe's early history, its precise age is still uncertain, since it may have originated at any point within the first 300 million years. The main infrared imager of the orbiting observatory, dubbed NIRCam, picked up Glass Z13 in so-called early release data, but the finding was not made public in the initial image set, released by NASA last week. 25 astronomers from across the world, including Rohan Naidu of the Harvard Center for Astrophysics, have collaborated to present their research in a peer-reviewed publication. The group looked through this far-off universe's infrared data, looking for a unique signal of very far-off galaxies. All photons or energy packets are absorbed by the neutral hydrogen of the universe between the object and the observer under a certain infrared wavelength threshold. They were able to determine the locations of these photon drop-offs and infer the presence of these most distant galaxies by analyzing data gathered through several infrared filters directed at the same region of space. For instance, considering how soon after the Big Bang it formed, the galaxy has a mass of 1 billion suns, which is probably quite shocking, and that is something we don't really understand. Let us know in the comments, what can we expect next from JWST?
So these are just comparing images from Webb and from Spitzer to show you the difference. Spitzer, nice picture, but a little blurry. Webb, highly defined. And this is what's giving us all the data, well, not all the data, but giving us what we need to figure out what's out there and what stars and galaxies contain, what elements, and could they contain life. Webb is also being turned inward to our solar system. So in these next pictures, Jupiter and its moon Europa are seen through the telescope, and Europa is a good candidate for some sort of alien life. When we talk about alien life, we typically think of life on planets, but moons are great candidates as well. There's Jupiter's moon Europa, and Saturn has Titan, and then my pick for the one in the solar system that has the most chance for having life is Enceladus, another moon of Saturn. And that's Jupiter as well. This is the Great Red Spot. The Great Red Spot is a storm that has been raging on Jupiter for 300 years. It seems to be dying down now, but it's a very powerful storm, and you could fit at least a couple of Earths within that one spot. Here's another picture of Jupiter with a red spot. And then these are the auroras that appear on Jupiter. Auroras are brought about by the interaction of the atmosphere with the photons that come off from the sun. So the aurora borealis that we have here on Earth, it's really an interaction of the sun's photons, which are packets of light, interacting with our atmosphere. And Photons are what bring the light to us. Photons can also move things. For example, we have spacecraft out there that are being powered by solar sails. Photons hit these sails and move the spacecraft along. And then this next picture is 365 light years away, and it's a baby, 15 to 20 million years old. When we talk about ages like this, these are really nothing compared to the universe when we talk about 13.8 billion years. So this is, up here is the star, and these are different ways of seeing that star. And then there's a planet in here. So these are taken by different instruments. The Phantom Galaxy, 32 million light years away. I think that's an outrageous picture.
Is that one galaxy?
That's one galaxy.
And it's called a spiral galaxy?
Phantom Galaxy is the official name. But there are spiral galaxies, of which the Milky Way is one. And it's a spiral galaxy because it looks like a pinwheel. We have the center, and then we have arms going around, just like a pinwheel. And we are in one of those arms, which is fortunate because it's just like, being in the city versus the suburbs. The middle of the galaxy is where everything is happening, where you don't want to be, because you've got a black hole, you've got black holes flying around, you've got things crashing into each other, just like the city. And now we're on the outer one of the arms, which is the suburb, a bit quieter. So this Tarantula Nebula is that. Again, a star nursery. How that looks like a tarantula, I don't know, but and this is a brown dwarf coming up. A brown dwarf is a failed star. It's a star that failed to grow up. And it's wrapped in sand-like silicate grains. It has water, methane, carbon monoxide, and all of those other elements that were detected. And astronomers have speculated that some type of brown dwarfs are turbulent and have turbulent atmospheres. And that's a brown dwarf star. The Orion Nebula. On the left, we'll see Hubble, and on the right, we'll see Webb. Again, the contrast. That's why Webb is so valuable.
In all those little white dots, the galaxies.
Yes. Okay. This is Webb taking a look at Mars. The left side is a graphic showing a close-up of Mars. It's taken by one of Webb's instruments. And the right side is a heat map. Everything generates heat. And in this particular case, we will see the heat generated by Mars. Anybody believe that life once existed on Mars? Mars was Earth-like before Earth came along. I'm betting on it. I'm hoping that we find something, but it was Earth-like at one point, and then it lost its atmosphere because it was too small to hold on to it. And this is where Webb took a shot of Neptune's 14 known moons. I'm not going to go through all of them. Well, 7 of them. Notice something around Neptune? A ring. Saturn's not the only one that has rings. The gas giants do. These are the pillars of creation. And there you go. We can actually look, well, in this one, we can actually look through the gas and dust to see the stars being formed. And then this is just a different picture of it, showing the layers of gas and dust. I think these are the most fascinating. In the next picture is massive gravity of galaxy cluster. I'm not going to go through all of that. It acts as a cosmic lens to bend and magnify light. That's what I was mentioning before. Light being bent. And galaxies, they come in clusters. So we're not, the Milky Way, for example, is not just the Milky Way. We're part of a family of galaxies, which is called a cluster. And these galaxies, because of gravity, they stay about in the same place in relation to each other, even though the universe is expanding. So a cluster would go along with the fabric of the universe, but it's still a cluster. And this is identifying two particular distant galaxies. And these may be the most distant starlight ever observed. This is an interesting one. There's a protostar in here that is only 100,000 years old. Only 100,000 years old. And it's right, you can't see it, but it's right in this neck right here. So taking a look at our solar system planets, looking at astrobiology, using biology to figure out what's on the other planets and whether they could hold life. So we have to decode a planet's atmosphere. And this is Earth. So for Earth, you see ozone, carbon dioxide, water. I don't know why they didn't list oxygen here, but there's oxygen, methane, which is a really good signature of life because methane is a byproduct of life. And these are just pictures of atmosphere compositions. Webb will also look at black holes. Black holes are the result of massive stars exploding. What happens, the way a star shines and stays stable is that there's gravity, which pulls it in. But then there's nuclear fusion, where hydrogen is fused into helium, and that has an outward push. So those two forces balance each other. When the star runs out of fuel and you can't get that push from the nuclear fusion, the star collapses. The shell of the star explodes, and the core becomes a black hole if the star is big enough. And it's called a black hole because the gravity is so intense that not even light can escape it. Gotcha. So here you can see black holes with a galaxy. And you don't want to go near a black hole because once you go in, it's like the Roach Motel. You don't check out.
How do they find these black holes? There's a lot of gravity, so they find it by,
Well, what happens with a black hole? Black hole has such strong gravity that stars fly around it. And if you see the motion of stars and they're going really quickly, that indicates that there's probably a black hole. Plus, it also emits light because around the black hole is all the material in what's known as an accretion disk. That's everything that the black hole is trying to suck in. And so it goes in a disk and it travels at very close to the speed of light. And as things travel fast, they emit light. So that's the way we look for it. And only a couple of years ago, we were able to photograph a black hole.
Estimate how many black holes are out there?
No, it's because you can't really see them. Can I do this? And these are galaxies merging. I'm going to go quickly through this after we see a couple of galaxies merging because we're running out of time. Okay, you can see these two galaxies, they're merging. This is what's going to happen to the Milky Way and the Andromeda galaxies. And basically on the other side, you'll see the same thing. This is a dwarf galaxy, which is just a small galaxy, 3 million light years away. Actually, that's a picture of the dwarf, of what's in the dwarf galaxy, all those stars. These are two blasts from newborn twin stars. You can see the blast coming out. There, there. We're already planning for the next telescope, and it's going to be liquid because liquid can magnify things. As you see on the right, that's an astronaut at the International Space Station. And as she's looking through a bubble of water, you could see more detail of her face. And there's Carl Sagan. I love this quote: "Somewhere something incredible is waiting to be known." We are a species of explorers. We want to know what's out there. And if you heard about the DART project, double asteroid redirection test, there was an asteroid called Dimorphos where we tested a spacecraft slamming into it to alter its course. And that's one way to deflect an asteroid so it does not hit Earth. The wrong thing to do is the Bruce Willis method, to blow it up, because now you've created a lot of other asteroids that are going to hit many places on the Earth. So one of the best ways to do it is with redirecting it by punching it, or another way that we're trying to devise is using a laser that will point at it and just shift it out of place. And that's what it looked like on the right-hand side. That is Dimorphos after we gave it an uppercut. And thank you.